Good afternoon, dear participants. Today, we have with us Dr. Krishna Baishnab from NIT Silchar. He is an associate professor in the Department of Electronics and Communication Engineering. I will briefly just introduce him. Dr. Krishnalal Baishnab has done his BE from NIT Silchar in the year 1995 and MTech from Indian Institute of Technology Kharagpur, West Bengal in the year 2004. He has done his PhD from NIT Silchar on the and his thesis is based on analog mixed VLSI for visual computation. His specialization is analog VLSI and RF design of continuous discrete time analog circuit for biomedical applications, RF CMOS circuit design. Today, he is going to speak on the topic of fundamentals of VLSI circuit design. So I will hand over this session to Baishnab sir so that he can deliver his talk. Thank you.
Yeah, thank you, Dr. Apurva, for inviting and giving me chance to share whatever I have with our beloved all the participants, most of the participants and faculty. It is my due respect to all. That's really is a good platform where we are meeting each other and we'll be really discussing many issues. Maybe I'm delivering I want that it should be interactive so that because we all are teachers and we have to stimulate the new minds, our students, and I like really the collaborations because collaborations makes the things because nowadays the trust area is Atmanirbhar, as our honorable PM says, that Atmanirbhar India. So in this context, we have to work and we have to stimulate our young minds, young students, so that we can have, because BLS started very late in India, but over the time SMDP and other Ministry of IT is taking initiative. Really, I think that's great things. The way having now Tata also starting this Fab Center at India and Noida. I hope that will be a new day and new sunrise for India in VLSI design. As Apurva said, the VLSI, fundamental VLSI, I was really a little bit doubt whether I should go with the analog side or digital side. So if I take both the things, it's become a very big peaks. There are many other speakers might be talking on different domain of device and other things. So especially a device aspect details I'm not going. I'll be taking just have a look into the basics parameters and aspects that we need for the circuit designs. Those aspects are need, and I'll move forward with our whatever I like to share with you. And if any doubt, please you can put forward your questions, please. Okay. Is it at Apurva fine from my side if I'm pushing onto this analog side much fundamental?
Yes, sir. It is okay, sir.
Okay, because there are many speakers maybe talking on the digital VLSI, I'm not touching, otherwise it will look too bulky. Can you tell me what is my permitted time so that I can wrap up on this time?
You can take, sir, 1 hour 45 minutes and you can reserve 15 minutes for question and answers.
Right. 2 hours I can take it now, almost.
Yes.
Huh?
Okay.
Yeah, thank you, please. Then I'm sharing my PPT and yeah, please, I'm sharing my PPT, please. I'm just taking a 1 minute, please. Yeah, that's the topic is fundamental of digital VLSI circuit designs. At the very outset, I take the outlines of this. You see, I just roughly written the things because I was not in a proper positions to check down the things. Maybe a little bit, but it's called scattered will be there in my content. But my theme is called basically circuit designs and fundamentals of circuit design. So what I thought of that. Yeah, I thought of. I thought of I'll just take the features of this important features of another circuit designs. Okay, then circuit designs, then frequency response and challenges. All those basically will be contained on my lectures. Okay, if I go to the next slide, you see introduction I'm giving. These are all basically we call very common word. I believe all of you know that. Very common word VLSI and ULSI, all sort of things that more than 10,000 of transistor we got VLSI. You see that if I expand also, we can see that number of transistor will be in a particular chip, and we have a die basically. That's other speaker may be talking on that. Basically, yeah, if I see the wafer, if I see a wafer, I'm just giving a just brief about the wafer so that I hope I can reach you more better way. Okay, I'm just taking a 1 minute, please. Okay, and I'll take a. I'll just move out and I'll just take a. Yeah, please. Yeah. See, basically wafer is like that. Wafer is like that, and we have a dies, and dies. These are the So this is wafer basically, and the VLSI design. This is wafer. This is fabrication that we do, and this is the die, and die basically silicon die. We call floor. So that's floor basically the challenging, and we need to design. We need to a particular floor to because a die will be there where we can put our all works in there. So like that, you are booking for one die, then you need to book entire die. Otherwise, you need to have an understanding among the some institutes. Then you can make your own die, and then finally you can have to segregate the work. Or in a particular chip, there are many works. You have to divide among the institutes or particular company where they're designing the chip. They have their own die, maybe one die, maybe two die. So how to put into the die cost is very high. Die cost is very high, and so the challenge for the design VLSI design engineer, how I can pack all my transistor in a particular die. So that's the things, and very important that the engineers are working to put all transistor in a particular die. If I go to the second die, the cost of the die will be cheap, will be more, and that's you cannot catch the market. So those challenges are there. Technology node, if I think of technology node, then we have 160, then we have a 30 technology node nanometer, then all other technology node where we can basically more says that, then we have a 90 nanometer, 65 nanometer, then we have a, I'm just giving a brief about the technology node that we have 45 nanometer gone. So that, and every nanometer you see that the number of transistor we are pushing into particular power unit area is double. That is the most says that from moving one node to another node. This is a node. We call every technology node is called node. So you are moving from one node to another node. So power unit area number of transistor that you are pushing is double. So that's you can have a more activities. If you can push more down transistor in power unit area, then your die size will be more compact, and your chip will be more compact. Okay, silicon floor will be more compact. So that's the challenge, and industry is working so that they are going down, and going down, there are so many advantages are there, because you need to have a frequency if you want to work in the high frequency operation, FT, because FT, if you talk about mobile applications, Apurva, am I fine? The way I'm moving, I'm going to my slide. Before that, I'm just giving intro.
It is okay, sir.
Yeah, please. See, that's what challenge is that today what we see, the mobile communication, everybody having the mobile, and those basically even fishermen, everybody having the mobile. This is basically 130 nanometers a back throw. Before that, it was basically BJT, where basically used for the RF applications. MOS was not suitable before 130 nanometer for RF applications. Point to be noted. RF application starts at 130 nanometer and downwards. So before that, it was MOS, and MOS was bulky, because those days of early of 90s, MOS basically not MOS, BGT was the most popular for the RF applications. All power amplifier and other things that designed for the application, those are basically for BJT, and cost was huge, and this is not reachable to the public. It was basically for the R&D centers and other particular companies where they need. So a lot of investment needed. So that market could not be caught because of cost involvement was there. The moment 130 nanometer has come, and the MOS has been used for the designing of the RF transmitter and receiver design, transceiver, what we call. And that is the breakthrough. That MOS fabrication is standard fabrication process. And since challenge because of capacitance and many other aspects, FT is a big issues. FT means transient frequency. Those days of before 130 nanometer, transient frequency was low, and because of that, it could not be useful for the RF applications. So a lot of research happened on the MOS modeling, and finally it is to 130 nanometer technology, where F2 achievable to 60, that what is called gigahertz range. What exactly we have a early mobile combination was 980 megahertz. What we started in 2G communication, we started 980 megahertz. And then we have a 50 megahertz bond was there. And between this, so it was 130 nanometer was very, very suitable for that. 130 nanometer was very suitable. And that's the breakthrough where really we can really see in the last 2 decades, we have seen the huge revolution in terms of the mobiles and data operations. People are not happy with the boy, then started with all more bandwidth, then technology down. So that's the challenge why basically we are going down the technology node. And as you know that in a mobile application, basically this is not only digital and analog, this is a mixed mode designs where we have to have everything. We have to have analog component, we have a digital component also. So that's the mobile is a mobile receiver or mobile set. We say that is a complete examples of really analog and mixed mode signal where basically we are using for entire processing. So that's now coming to that one. I just brief about the what the die. We must know the knowledge of die, and we must know the die. And I said that 130 nanometer is a really breakthrough. Remember, is a breakthrough for mobile applications. Presently, we have a 11 nanometer technology, so that's more challenge and have in terms of stability. And the device people will be talking much on the device aspects. How this nanometer technology, 11 nanometer technology may be suitable for the futures, and maybe they are going down, but without with some other directives, not in terms of silicon dioxide, maybe some other directives. You see, my talk is basically I'm assuming that all are familiar with a little bit idea of because all are faculty. So that context I started. Okay, I'm not going to not gone to the MOS exactly. MOS, all of us know that what is a MOS 3 or 4 terminal device. So that's now again I am moving to my PPT. Sorry. So if I go to my if I go to my this one, just a minute. Good. So that's I'm saying that VLSI designs. So we are here actually VLSI designs. So that's Intel has prepared. You see, there is example they have given. Now, I already said the Moore's law says that please point to be noted the power for moving from one technology node to another technology node, number of transistor is double in a power unit area. They have meant that 26 months. Somebody says 1 and maybe 18 months. Okay. So that shows the straight line that exactly given. So we are following. They have given examples of so many examples. They have given Pentium. You see Intel 486. So many transistors given. That's predicted. So what summary things we must remember that the number of transistor per unit area, number of transistor per unit area, transistors per unit area is double basically, double. So that is the fundamental things basically Moore says, and we are following. Now, this basically another example, just motivations. Why basically analog is so important in front end design. Back end we do have digital side and other things, but analog we prefer in the front end, and it makes it very complex size and power consumption also less. And if you go to digital, you know that we need to have a ADC, then we need a conversion. So a lot of bulky memory is needed. It becomes a bulky, but yeah, that is a lot of flexibility in terms of cancellation, adaptations, then the blinks, all sort of facilities are there in a digital circuit, but analog may not have that much of flexibility. So people prefer to have what? Digital side, but front end is analog, so we need to have analog again. Now, this is the spectrum, just motivation factor of what I am saying. What is the motivations of working on the analog side? Again, I am saying, please remember, many of my circuit, many of my figure, I am not giving citation, I am excuse for that. Basically, all are taken from few books, maybe Rajabi books, maybe Becker books, maybe Allen books. So these are the a few books that I used to have. Please, so my circuit diagram, my figure, my equation, maybe from those books, please. So these are circuit diagrams and other picture is not my mind. So I just copied from some sources. Maybe this is from Becker book, Becker for CMOS circuit design. So this please point to be noted. Now, what is my objective? Why we are going for the digital communication, analog communications, and analogs, not analog communication, analog VLSI circuit design. Where is the scope? You see that. Again, I said that analog basically front-end design, where we prefer to have front-end design. Now, why I am given these diagrams or travel to you, see that those are the basically frequency range where there are several applications are there, and we can design our own circuit for those applications. Now you see that wireless communication, we are saying 5 to 6, 5.5 gigahertz. So we have to have our amplifier and other circuit at 5.5. So how to work this 5.5? Now we have some audible frequency 20 is more challenging, okay, because 20 hertz circuit design, another challenge is flicker noise will come into picture, okay, and at high frequency again thermal noise will come into picture, and low frequency flicker noise, so very challenging, and low and high also. And the mid-band is very good designing. Mid-band frequency design is very simple, okay, so people do the mid-band frequency design. And what we study in our undergraduate courses, basically those are mid-band frequency or kilohertz to megahertz range circuit designs we do. But if you want to go beyond that, then circuit design is complicated. A lot of complications are there. So we'll be learning what is the challenge. So you see that certain equations are given. What is the meaning of these equations? Very important. See, the moment I say I naught by II, this is called output and input current. When it is become weak, we call it as FT. We call it as FT. What is FT? Transient frequency. Where this frequency at which your output current and input current ratio becomes 1. That is called FT frequency. And the first pole that is locating, if I say frequency over here, and then first pole you will locate. If is FT is here, if I say FT is 1 gigahertz, then my first pole will be full. Pole will be at 51 means 1 by 2. 1 by 2 gigahertz means around to be 1 by 2 gigahertz, half 1 by 2 gigahertz. The first pole will be located at 1 to 1 gigahertz. Means it is how much? It is 500 megahertz. It is 500 megahertz. So those at 500 megahertz, your first pole is coming. So bandwidth is, you can estimate your bandwidth for that. So that way, we have to have high FT to work in the higher frequency region. And what is the challenge in the FT? You see that equation, given FT equation. Then you see that very important parameter L. L is the length of the channel of the MOS. All of us know what is a MOS. And this is the source, and this is the drain, and this is called length of the channel. I'm not taking overlap and other things. I just took the simple one. Okay, I just took the simple one. Yeah. So I just took the simple one. This is the basically you have your what is called, yeah, you can yeah, and then we have a 4 terminal. Obviously we have terminals, and then body will be there. I'm not doing okay, body. This is the body, so body connection also needed. That's all of us understood from circuit point of view. This is the gate. So you see the L in FT, what I understood that L is a basic critical parameter. L square. If L is high, you understood FT is low. But if L is low, FT is high. So I can reduce L. Reduce L means reduce the what is called MOS dimension. See, if I say Apurva, any question? And hello Apurva.
Yes, sir.
If any question, please, from audience.
Okay, I would like to request the participants to raise any questions if have any. Interrupting sir, you can raise the questions.
Yeah, please, always welcome, please. Okay, please, I'm proceeding then. Now, all of us know basically the MOS. We have a MOS. I'm just drawing a small MOS. It is a source, it is a drain, and this is the your channel oxide. This is the channel, maybe different. I'll take different color. If I take different color, this could be the channel, and this is the channel, and this could be the another body. Body will be there. So this is the MOS structure that I can just roughly say that. This is called length. This is called length of the channel. So now you see that what I understood from this MOS structure, that if I have L reduce, I can have high FT. High FT means I can work in the higher frequencies. So understood why people are moving down technology node. As I said earlier, that we have 180 nanometer, then 90 nanometer, 130 nanometer, please. 130 nanometer. We have 130 nanometer. Okay. I have 130 nanometer. Then we have a 90 nanometer. Then we have a 65 nanometer. 65 nanometer. Then we have a 45 nanometer. So many technology nodes. I already said, once we move from one node to another node, I am doubling the what is the number of transistor permanent area. Permanent area. In permanent area, I am doubling the what's called number of transistor. So that is the objective. This is the theme of our what's called VLSI designs, as already shown by the diagram also. Okay. Moore's law. So now you understood that L is less, so I can work in high frequency. So to work in those higher frequency, I have to reduce my L. And that is the demand why people are going down. Because you see, those bands are now highly crowded. You see, talk about 1 gigahertz mobile communication, everywhere mobile communication. Then you think about, you see that they have not mentioned, there are so many applications that are military operations happening, ultra wideband communication happening. You have 3 to 10 gigahertz. So while K-band, X-band, all are spread over the gigahertz. So these are basically crowded regions where most of the people are working on those because line of sight communication. You need less antenna size. If you work in the low frequency, again antenna size will be high. All of you know, we have seen that our TV station and other, this is a long tower in it, because low frequency means antenna is high. If you have a high frequency means antenna size is less. So antenna size and the frequency operation is inversely proportional to each other. So why people are going for high frequency? One is line of sight communication. If a low frequency, it is a sky communication. We have to reflection on the ionosphere, then it will go on spreading. And very low frequency, it is a ground wave communication. So people go for the line of sight communication at gigahertz range, higher megahertz range. So line of sight communication is preferable. Secondly, thing is that to work in the line of sight communication, I have to use high FT. And that's, I said, the 130 million nanometer is a breakthrough for work in the RF domain. And then we have this other parameter which is constant for you, because BGS is okay. BGS one overdrive voltage, you have to have some high overdrive voltage. That doesn't much significant. Most significant part is L. So L have to reduce. So now what we summarize, that the technology node that we have to reduce, or have to shrink down. I should not say reduce, shrink down, so that I can work in the higher frequency. Now you see that Government of India has given 60 gigahertz a free band. Why 60 gigahertz free band? If I see my next slide, or I have given one more slide. Let me check one slide I have added. Yeah. See, I'm going back. Now, Government of India has given that 60 gigahertz free, because 60 gigahertz not suitable for outdoor communication. You see the attenuation. 60 gigahertz attenuation is very high, and whatever we have, we call Wi-Fi band or ISM band. Another frequency in industry, basically we call ISM band. ISM band is called industry, science, scientific and medical science. This band is basically 2.4 gigahertz. All of you know, this is basically a free band, no license is required. ISM band, industry, scientific and medical science. These three bands are Government of India has given free. Anybody can use any design. Our own home appliance and radio operations, not home appliances and remotes and other, all are basically in 2.4 gigahertz. We have an induction heater; those are working in again 2.4 gigahertz. So basically, those are basically ISM band. Now, why ISM band? And ISM band also is not a given shown here. At 2.4 gigahertz, there are certain peaks are there, not shown over here. Okay, some peaks are there. So those peaks are basically affected by the water molecules and oxygen molecules. So those are basically not suitable for the, again, not given in this picture, but there is another affected by the water molecules, 2.4. So Government of India has given 2.4 for wireless personal network. What's the wireless personal network? Means for indoor communication or WLAN. For WLAN operation, they have given 2.4 as a free license. You can do indoor operation, because oxygen molecules and water drops are not coming into picture for circuit designs at those frequencies. And now talk about 60 gigahertz, you see the 60 gigahertz, you see that again there's a peaks, nobody will purchase 60 gigahertz, because revenue generation basically comes from the frequency. So Government of India basically sell those band, maybe ATAL, maybe Jio, maybe so many vendors are there. They're looking for the channels to operate, and they have to pay huge revenue to Government of India to get the license for those. And that's then again a 60 gigahertz Government of India has given few years back, given that okay, you can use this as a free band. Because you see that these bands are very high attenuation at open air, so not suitable for WPAN outside. So these are again, you can go for indoor communications. So now I understood that at 60 gigahertz I have a free, I can design, license, circuit, but I don't need to take a license. Obviously, wherever I need to license, I have to use a lot of money investment. But 60 gigahertz, no, because what is the advantage of 60 gigahertz is that those frequency completely free, noise is less because number of users is less. You have a new city where no traffics, obviously, so good communication. But if you are in a bustling city like Silchar and other Gauhati, obviously traffic will be more, and you know that communication is difficult. So 60 gigahertz is a new domain where a lot of challenge to circuit designs, and now people are working to design circuit at 60 gigahertz. But 60 gigahertz circuit design is very, very challenging. Okay. We studied basic amplifiers, but those basically for mid-band frequency, maybe few kilohertz. But what are the challenge for work in the higher frequency, RF frequency? Those basically are the subject or topic to discuss a lot. But as I was asked to have a basic on the analog circuit, I'm touching on the basic stuff. But I've just given the themes where we can work together. And this is a virgin domain, 60 gigahertz design for the communication. So that's a wonderful area where we can work together. 60 gigahertz circuit design at 60 gigahertz. Okay, so now coming to my that's I already said. Now, as I said, that analog circuit basically where we can put our analog circuit is basically we can have a transmitter, receiver. I've just shown you examples of do whatever we are doing basically in communication. We studied, we design our own circuit in analog or digital base or whatever. The enter part that I am showing you, enter part whatever I am showing you, this is basically transmitter, this is basically, this is also a transmitter, both are actually transmitter they are showing. But what happened, here they are showing driver and no driver. Without driver is not possible to drive an antenna, because antenna is very, again, antenna is very low input impedance. So to drive low impedance, I need to have a power amplifier design. So power amplifier design also is very challenging, how you design power amplifier. But designing power amplifier, again, questions come at what frequency, very important. Whether it is a low frequency, high frequency. High frequency power amplifier designing is very, very challenging. So those, again, area where we work together, a lot of opportunity for the new generation to work with the power amplifier design, because earlier it was a super hydrogen receiver, but those days, nowadays, no super hydrogen receiver direct conversion. There is no higher band. Directly, we have RF signal directly convert to the baseband signal. So those things we have to have, because if you convert directly to RF2, earlier you remember we studied the RF signal is there, then we have to convert into IF signal, intermediate frequency, then we have to go to the baseband signal. What we call super hydrogen receiver. Should I write the word somewhere? Super hydrogen receiver, basically we have RF, then we have IF, then we have a baseband. Those is called super hydrogen receiver in nature, but those are gone. IF is reduced, cancel. Directly we are going where? Directly we are going to have, directly we have a RF2 what? RF2 direct to baseband. Baseband understood base signal. So that is a very challenging how we design a receiver. What basically nowadays we are using in the mobile, all are basically direct receiver. There is no intermediate frequency over here. So this basically just to have a look into that, just to have a motivate you that where you can work. We can work. This is a mixture. This is called mixture. This is oscillator, but this is called mixture. My mixture. So designing a mixture also challenging. Mixture is a nonlinear device. Mixture is a nonlinear device. So we need to know the nonlinear behavior of all those RF signal. Okay. So now this is our motivation part is over. Any question from motivation, please? Dr. Apurva, any question from audience? Are you getting any question? No.
No, sir. They have not raised any question yet, but participants can raise their question.
Please, I am proceeding then. Okay.
Okay.
Fine. Because sometimes you ask question, I feel okay. They are still after lunch now, so people maybe a little bit, okay, no problem. I'll just continue, please. So, my theme of my this picture that I have shown you just to motivate. Then we can work a design. We can work for the mixture design. We can work for the oscillator. We can design for the amplifier. So there are a lot of things are there. This is antenna design. Other people, there are antenna group is there who design the antennas. Fine. So how we will start? Now you see another example. I am giving very important example. See, for any other application, LC tank is very important. LC tank, we call LC tank, LC tank. So resonant frequency is there, very important. So now to realize capacitance, we basically use a MOS for the capacitance, MOS. So we must know the what basically capacitance is a variable capacitance. How I can change the we call MOS capacitance, MOS capacitance, MOS capacitance, capacitance. Okay, so basically this why I'm showing the picture. Picture is meaning is that we are designing LC tank where we need capacitance and inductance, and you know that every application nowadays we are going for the basically for on chip. What is called on chip? On chip means all my circuit should be on the inside the chip. So now none of the passive devices are available in the chip. Passive device cannot be put into the chip. So the diagram that we showed basically is a passive device, but these are replaced by the MOS. Inductor also we can design by OTA. There are so many active inductors are there. So there are other chapters, you will find another books will be there. Inductor design by using active OTA, or we call active OTA. What call? Active OTA, active OTA. I'm just giving the name, please. To the interested, you can work with the active OTA, active inductor. So we'll replace the passive inductor. What we studied? Resistance. We studied capacitance, we studied inductor. All are basically passive, what we studied in the VTech level. What is a passive? We have to replace by using what? CMOS circuit. Okay. And very well known that MOS capacitance. That MOS can be used as a capacitor. MOS can be used as a resistance. MOS can be used as an inductor. This is the theme of analog circuit design. That how can I use MOS as a resistance? How can I use MOS as a capacitance? How can I use MOS as an inductor? So MOS as an inductor basically takes a lot of silicon area. If I don't use an active inductor, I can design inductor by using other ways, but it takes a lot of silicon area. If I have a chip, so I have a chip, inductor will take entire volume. Entire volume will take, and inductor will take entire volume will be taken by inductor. Other component will take just the minimum area. What area? Just a minimum area. Understood? So this is the basically, this may be the inductor, rest part of the circuit will be this. So that is not advisable. Good. In a die, entire part is your inductor, and one part is very small or negligible part, maybe 1%, maybe 2%, maybe 5% is your circuit design. So that's really consuming the major my silicon area. So that's why passive inductor is not at all used. So we have to replace the passive inductor, we call active inductor. You can have a separate book for that. Please, you can have a internet also. You can, if you search active inductor, they basically use OTA. OTA means operation tense conductance amplifier. I'll just show you the, lastly, I'll show you one just brief. OTA basically, OTA means operational transconductance amplifier, OTA. OTA is a huge applications in a analog circuit design, and maybe designed for the amplifier, maybe used to have filters, used to have many things, current source, many things. So maybe used for the what is inductor also. I'll show you. So let's do. But the theme of my this slide is that that we have to replace C by MOS, we have to inductor by OTA or call active, whatever call active inductor. So those basically part of your analog circuit design, that active inductor, how you design the active inductors. Okay, so I'm proceeding slowly because if you want to know OTA, then you have to know differential amplifier. Then so many things will be there. Okay, so stay tuned. I'm not coming OTA directly. I'll go slowly. Then I'll move into the OTA jump. Okay, clear to my side. Okay, now my second picture. You see that what I'm written in the second picture. I already said that my what is OTA, that is a yeah, MOS. So please. Now, here you see, we can see here, you see the MOS, this is the MOS structures. We have a different types of what is called 4 terminal, I already said that 1, 2, 3, 4 terminals. And you see that the certain are gate connected with the gate. So these are basically for a gate capacitance. What capacitance? So you see, if I write GD, CGD, if I write CGS, GB, these are basically what you see that, gate connected, na? Gate body. I'm not writing B, at least I write GB. So these two basically, is there any? No. These two basically gate capacitors. These are sorry. These are basically linear. These are basically what? Linear nature. These are basically linear nature, because all of you know the CGD is equal to maybe 2 by 3 of COX. Something will be there, maybe 1 by 3 dx. Particular regions, maybe CGS, it is 1 by 3. CGS maybe is 1 by 2 by 3 of COX. These are the basically completely linear nature. COX basically, what I call COX basically, we have a MOS. If I take a MOS, this source and drain, this is my oxide layer, the oxide layer. So obviously there is a capacitance. Since there is an oxide layer, this is a polysilicon. Beyond that, this is a polysilicon. What is silicon? Polysilicon. Poly, and this is your substrate. Okay, substrate. So that's basically gives you a capacitance. I have a diagram. I'll show you. So those basically, capacitance we need to evaluate. There are certain capacitance. This capacitance are linear. But wherever there is a body, written, body, B, GB, CGB, CSB, all are basically parasitic capacitance. They are not linear, their expressions are different. Okay. See, this is the diagram that I'm trying to show you. What you have to have some visualization that C1 and C2 basically these are parallel, these are in series in nature. This is basically oxide and this is basically polysilicon. Okay, this is the channel and this is the substrate. This is substrate. Now understood? If I have divide the region, I can have what is that? I can have region 1, I can have a region 2, I can have a region 3, then I can region 4. So 4 regions where I can really I can place region 1, region 2, region 3, region 4. So now we have studied parallel capacitance in our class HS. So those are called basically capacitance, and wherever there is a parasitic capacitance equation is nonlinear equations, because if we see the diode, if I see the diode, we have N type, we have P type, and there is a junction form. So this capacitance is what? Parasitic capacitance. What capacitance? Parasitic. Sorry. Parasitic capacitance. Parasitic capacitance. Okay. So wherever there is a body, it will be parasitic capacitance. Okay. I'm just briefly saying because I'll be moving to the circuit part. So I need to have an equation also that's parasitic. That's picture shown you that if I have a MOS and if I configuration this, I can, because BG change, my MOS will be location will be different. BG is less than this one, it is a off stage. Then off stage. Off means this is saturation, this is triad region. See that? If I give a very high pulse, means it is going to the triad region. Remember, if a MOS, if I give a pulse signal over here, big pulse. Pulse means it is around to a BDD or BD, whatever, or BD, whatever given in the books. It is, sorry. Okay. So it is what? Basically, if I give a big signal means, large signal means it is coming to the triad region. Whenever we are giving a pulse at the MOS, it becomes a triad region. If it is a moderate BGS, input signal, moderate in BGS means I can take as input also. I can say it is a bean, say bean. Understood? So I can show you like that. I have a MOS, sorry. I can show you like that. I have a MOS structure. If I give a bean over here, bean plus minus, grounded, and I can have something RD over here, doesn't matter, whatever. RD. So if I have, you see, if I give a big signal over here, if I give a pulse at a certain moment, at this moment, MOS will be triad region. At this moment, at this time. So remember, high pulse means it is in triad region. Triad region capacitance, you see this, and saturation region, basically there are two parts, this and this part. So that's, you have to have circuit region, you have to idea where I need to have, okay. Now, very important, I said you that MOS can be used as a resistance, MOS can be as a capacitance. MOS can show you that MOS can be put into the capacitance, because again I am showing you. In the case of MOS as a capacitance, what I do, that when I have a source, sorry, I'll take a different pen, it will be good looking, I believe. Yeah, it is a body, then I have a source, then I have a channel, then I have what? This is my source, drain, and this is my body. So this is body. So what I do, I'll short these two, okay? I'll short those two, this and this, there are two potential will be there, plus minus, and that becomes a what? MOS capacitance. Okay, MOS capacitance, I can make it. Body is also there, because body and source are connected. I can put some voltage over here, and here also another. So that become a what? MOS capacitance. I can make the MOS. You can check it, MOS capacitance. So MOS capacitance we can use as a capacitance, and here you see MOS can be used as a resistance. MOS can be used, very important. MOS can be used as a current source. Here is a current source they have shown you. Current source means it's a high input impedance, high what is called impedance, output impedance device. Current source means it is a very high output impedance. You see the current source, remember, current source means there are high output current. So output current is equal to resistance equal to, this is the formula that basically we can think of, okay, lambda ID. And if I have, you see, I am just giving a diagram that I have a MOS, and if I short these two, short to these two, this becomes a resistance. What is 1 by GM? 1 by GM transconductance. But if I put a MOS as a like that, if I put a MOS like that, MOS has transistors. If I put like that, and then you see this is, and I am giving some biasing voltage over here, some biasing voltage. Then this is nothing. This is another resistance, but it is R naught. What is R naught? R naught is equal to 1 by lambda ID. 1 by lambda ID. So remember, so MOS can be replaced. You see that GN by, all of you know GM is basically transconductance. It has an expression is there. Okay, so GM is equal to, all of us know that GM we can derive, and you can find out some formula is there. Mu x COX W by L into ID. So this is the basically GM. And if I see that in GM also, if I have a WI is high, my GM is high, ID is high, GM is high. So, but resistance is something different. 1 by GM is called resistance. So this is a very important formula theme, what exactly I'm trying to show you. There is a MOS, and if I connect the gate and drain, then it becomes a resistance. What resistance? 1 by Gm. What is Gm? Mu x, mu x and cox basically is not clear, or I'm just writing it another way. Yeah, please. It is mu x or mu whatever you write. Mu n, mu p, whatever. Okay, mu n. So mu n. Okay, mu n means n type. I write mu n. Okay, and cox means sorry, capacitance. COX. So this is basically technology parameter. A particular technology node has some value. Okay, maybe at 19 nanometer, at 118 nanometer, I still remember the data. At 30, at 100, 18 nanometer, at nanometer, this mu x, ux below, this below, only this part. Yeah, only this part below, this below is 355 micrometer, micrometer volt, and something unit will be there. I forgot the unit, sorry. So remember that some value will be there. So this is called technology parameter, sorry. What is called technology parameter? Technology parameter. And based on technology, the value will be changed. So what is with the designer? Designer are with WL into ID. W into ID. Hello. Hello. Who are showing? Yeah, sorry for interruption, please. Please. Now we understood that how important that we must know, we must convert. What I said, you see, this is nothing, this diagram that what they have given. Sorry. Diagram that given, okay, them. So I made a current source, and then become current source means high resistance. So this I have shown you, okay. So now understood, if I have somebody, this is very important, if I connect the gate and source in this diagram, then it becomes 1 by Gm. Even I can change another way. I can change in PMOS if I do other way. For NMOS, you see, if I do PMOS, Dr. Opurva, I'm just covering basics parts, okay?
Okay, sir. You have a question in the chat box, sir.
Oh, question. Yeah, right. Thank you for putting me. Yeah, chat box question. Let me check. Okay. Oh, Shakur Kumar Bora. Yeah. What is the area and power requirement of MOS capacitance while designing the layout for fabrications? And are there any advantages of using an NMOS, NMOS cap and our PMOS cap? Okay. Right question. Yeah. Yeah, I am moving to that one. Yeah, thank you for the really good questions that there. What Shekhar Shumon, uh, Shekhar Shumon Bora said. No, I'm just answering this question. Shekhar, sorry. Yeah, yeah. And then you see, yeah. Let me check again. Yeah. First question is that area and power requirement of the MOS capacitor. Basically, you see, MOS, it takes a very small area, obviously, but based on your WL, what basically WL you are taking, because W into L is a deciding factor. I already shown you what is GM. GM is a returns conductance. I already shown my diagram also. I have shown you. The GM is basically, if I draw GM, if I write GM is equal to what? You see that we write, we have a mu x or mu n, whatever, COX, and then we have a WL into L into ID. So basically, this is a deciding factor how much area is needed for the MOS. If I have used less WIL, it will take what? Less area. Less area. Okay. But your design may not permit to have a minimum area, or it may demand you to have a higher area because you need gain. Gain means I need to have a WIL high ratio. Okay, W into L ratio, not area. W by L ratio should be high. That a context. And another question I can see, yeah. Then what is the area power requirement? Power is, you see, always minimum, okay. And for a particular transistor, you have to have complete circuit design. Then you can say that what is the area required, because maybe you need to have a micro watt, maybe you need to have a milliwatt range. So that is your target requirement. What exactly you need for that particular circuit you are designing. Not for a particular MOS, because MOS is a component in a circuit design. There are so many MOS will be there, so that is a deciding factor. Power consumption. Maybe we have two types of power consumption. You have a static and dynamic power consumption. So if circuit is basically for digital circuit where there is a pulse operation happening, we have to have dynamic and static power dissipation. Analog also we have both the things, and then we need to calculate total power consumption per particular circuit. And then what you said, again another question, I can see the MOS capacitance while designing the layout for the fabrication. Okay, layout for the layout, you see the MOS fabrication is what? Whenever you are crossing N division and polysilicon makes you NMOS, okay? That is the fabrication process. But in a circuit design, basically we have to have so many transistors, and we need to put them into the line. That's the way we design this VLSI circuit layout design. Layout design, basically whenever NMOS and N diffusion and P diffusion, not P diffusion, whenever I see that you have an N diffusion, I'm just showing you, just please, if you can have a red pen. You see, maybe I can take different pen. This is my N diffusion, and if I have take poly like that, poly, that's mix one source and okay. But I can have a more number of what? Poly, so I can have more number of transistors, okay. So source in, and then what sort of combination, whether a series combination or parallel combination, those basically we work in the digital circuit design. Because to layout of an AND gate, NOR gate, all sort of things, and I have to find out the area of particular gates. I hope so that analog part we have done a lot of things. Then we have annual, we have to put into the annual, then we have to know the mid law, we have to know the what is called layout design rule. Yeah, then Apurva, sorry. Then you see that all are basically digital domain that we talk about. I did not touch much on that because those are basically, you can take a lot of time. I'm trying to push into the analog side. Huh? Please forgive me if I not cover those part again. Okay. So you see that polysilicon and polysilicon source drain, I can make source drain. Now depend upon what combination I want. Whether I want MOS like that, series connection, or I MOS should be in parallel connection. This is series connection. But again, MOS may be the connected like that. One MOS here, okay, another MOS may be connected over here, and both are in the same point. So that's another parallel combination. So parallel combination, your nomenclature will be different. So that's where we can design the layout and we can find out length. This is the length and this is the breadth. This gives you the, and Harish books, Harish and what? Western Heritage books has given wonderful starting, and you have to work. I hope so that you can design any logic circuit as a layout design. Okay. Now another question I'll take. Yeah, Apurva, my topic area is fine. Analog domain, or I should touch on the digital side also much.
Sir, it is better to touch the analog part because our FDP is only oriented on analog design.
Right. Thank you for that. Okay. So I touch on the analog part, please. Okay. So now then I'm not moving much on that. Okay, and digital part. Okay. Another question I can see. Yeah, MOS capacitor designing. Is there any advantage of using NMOS cap and PMOS cap? Basically, we prefer to NMOS cap. Okay, NMOS cap. NMOS cap we prefer. So those people are working on this layout design. There are more options are there. Basically, we popular with NMOS cap. Okay. What is another saying? Hirak Jyoti Goswami attendance link. Acha, okay. Whether the FinFET technology replace CMOS. You see, FinFET is still not commercially viable. Okay. People are working, I'm not saying the large scale production is still not FinFET. FinFET is basically before taking industry to production, it takes a lot of standardization process. Okay, somewhere people started. I'm not saying they're not started, but still CMOS is the most popular. But with the time, I think technology has to improve. I think they're improving. Maybe certain fab they started FinFET, but CMOS is most popular. FinFET is what extension of what is called CMOS. Only thing is that all are silicons, but whenever you take composite materials, then fabrication will be different. Otherwise, yeah. Sorry for interruption, please. Yeah, I can see that. Yeah, FinFET technology. Fine then. I hope I could able to answer your question. If I not, yeah, please. I'm just moving to my domain. What exactly I can see. Many people are here. When I present, actually, I cannot see. As nice to see, Covid. Thank you, sir. Okay, thank you. Fine. Okay, fine. Then I'm moving to my area. Yeah. Now what I realized that I can design my resistance by using MOS, maybe high resistance, maybe low resistance. That's all basically circuit designer can think of. Already said that I'm not talking about Horish Kitab, Horish books, other, because there is a digital side. As coordinator said, I must be in the analog. I am moving to the analog. Okay, much on that. So what is my target? You see that our target is to design resistance. You see that this is a resistance, this is a resistance, this is a resistance, and this is nothing owned by GM. And what is GM? This is GM. See that. Who control the resistance? GM, these two are technology parameter, technology dependent, technology dependent. So you have nothing to do with this one. For designer, you have two things. For designer, you have two things. You have these two parameter, very designer parameter. Designer parameter. Okay. Designer can control GM by what, WIL and ID. If you give WIL, obviously our GD will be high, but it will take more area. Okay. So remember, W high means generally in design, basically we keep L as a constant. With changing L very, very risky. Again, I am point to be noted. In a circuit design, because you know that analog circuit design is very complicated, because the bias point and every node has some voltage and current, and those will be changed if you keep on changing the MOS L. And taking a stabilized point, even to work in subthreshold region also very challenging. We keep on changing L. So what we do for preferable design, we keep L as a constant, keep on changing W only. Okay, even though it is W by L, we call it W. L is a fixed, we call, with general in circuit design, and keep on changing WL. There is more worth. So don't touch on L. L you keep somewhere and then keep on varying W, and you can have a different variables. So what you do, then we change the W and we get a different GM. And we can change ID, I can define GM. But if I change W, you remember my area of MOS will be more. MOS will be bulky, it will take more area and more power. So those parameter trade-off we need to have designing those circuit designs. Okay. Just already I explained this advantage, I should not say. These are all I can say that abstract level we have. I already said that my materials may not be in a correct order, but yeah, you see that abstract level we can have a MOS, then we have a circuit, then we have a gate, then we have modules, then all systems levels. Okay, everywhere I can do the optimization. I can do the optimization in a device level also. I can optimization in circuit level also. I can design optimization in the gate level. I can design all sort of levels. So these are coming digital common domain. I'm not watching on that. Okay. So again, these are the basic things. I think many other speakers will talks, or maybe circuit people, design device people will talk on that. I'm not touching much on that. Okay. So now, very important things here. You see that how we can change the BGS, BGN. You see that this is the very straight line graph, BD versus ID, that gives the resistance. I can make that if I keep the BG fixed here, and if I keep BD also constant vary, and I can have different idea on this graph. So different way I can have a what graph. So every graph we can say linear. Here also say linear. So that gives a resistance, one by resistance. So you see, understood. So that is the diagrams where we can play with the MOS and we can have a different. And yeah, this is the things I am showing. Here also the effect, you see that this is BG versus IG and BD versus ID. This is the output graph, and this is called transfer graph, transfer functions. See the diagram itself implied that If you keep on changing the length, you see that your graph will be down. Graph will be down. Then that is all mathematics, what will affect the graphs on the ground. So that's again shows you, if I even W change, you see that my graph is changing. So effect of W, just showing the W effect, and then you have a width effect, I mean thickness effect, length effect. Those effect basically shown. Please refer the books of Rajabi. What books? Rajabi. Please, all picture I copied from Rajabi, please. Rajabi. Rajavi, there are two books. One is called Microelectronics by Rajavi, another is called Rajavi Analog Circuit Designs. I took it from Analog Circuit Design. Okay, you can copy also, you can check it also. Okay, there are Rajavi is very fundamental books for circuit design and VLSI circuit design, and please look into that. And all those pictures basically copied from. I already said that we are just analyzing the effect of length effect and oxide thickness. So the length is changing, then you see that current is how it is changing. Okay, we have, this is the length, this is the higher length, so there is a changing. Width is this less, higher width this is. Again you see the length is less, length is higher, effect is less. Length is width is less, no, thickness is less, thickness is higher. This is the effect. So four effect I have shown over here. Please and check it from Rajabi. Those are interested in analog circuit design. Please follow the books of Rajabi Microelectronics. Then you go to the next chapter. Is called, next book is called Rajabi by Rajabi. Book's name is you have to have analog VLSI circuit design something. Third book is called RF design for the Rajabi. So those are people from communications. You can work with VLSI for communication. Very interesting domain. We have to have knowledge on the analog circuit and communication also, and a wonderful job to design in the communication for VLSI for communication. Yeah. So now again, it is shown the if a width is changing, with this is the width. So then the effect is shown you. Okay, in the Buddha graph, BG versus ID graph and BDD versus ID graph. So that's, so you have to visualize the things, and then this is a basically effect of body bias. BT changing is not desirable, remember. So that's is showing that. See that SB is 0, so everything is 0. So BTH equal to BT 0. But SB is some voltage. SB means source and body. Source and voltage is some voltage. Then I hope so you understood what is source and body. This is my source, this is my body. If have some sort of voltage over there, then it's risky. But if I short it, then there is no body effect. Okay, this is the meaning. So here source is grounded. If I put ground, then my problem is solved. Then problem is solved. Okay. So what I'll do? Yes, madam. Please. Yeah. So then, what is my slide here? So now understood that if I connect source and body together and grounded, then I can remove this body effect. So most of the design you will find that if I take a MOS, what I do, if it is NMOS, and this is a ground, what I do in circuit design, we'll short it. No body effect. And if it is a PMOS, and PMOS generally connect to the body BDD. So if it is PMOS, obviously I have a source, this is source, this is other part maybe there, okay? And this is a gate, so here body is connected to PD. So in a circuit design, you will find that generally PMOS we put in the NATO BDD. I'm just showing you one amplifier design. Amplifier design, simple amplifier design. What I will do, I'll take diver as a NMOS, diver transistor, and put in the ground. And I'll make, this is my output, and here I make my PMOS circuit. What I'll do, see that, this is my BDD, BDD means terminal voltage. Here they have written BD, but I am writing BDD standard. So this is my gate and this is my source. Okay. What I do, you see that generally I can put into that way, I can put this is B in, I can put BB, some biasing voltage. This is also resistance. I already said you that the few things you must remember, please, that if I take a MOS, if I short it, this is a resistance. Already said, these things you should remember, this is nothing 1 by GM. But if I take a MOS like that, and if I take some biasing voltage over here, MOS in some biasing voltage, okay? And then what is the Mason saturation? Then this is nothing a resistance, but high resistance, R0. This is R0. So R0 equal to 1 by lambda ID. So please remember these two terms, very important for me, for us, that a MOS is a resistance. Hello? Telephone. Yeah. Sorry, sir, I'll give you right now in presentation. I'll share. Okay, online, please. Huh? Thank you. Okay, please. Okay, so yeah. Then understood that. Am I disconnected? No, sorry, please. Okay. So now these two terms, you every time it will really come into picture. You should remember this is a current source. Second one is current source. First one is simply resistance. Current source means high resistance. Resistance is very high. High resistance. Here is a low resistance. 1 by GM basically low resistance. Now we see that this might be in, this is my some voltage I'm giving, it is become a resistance. Nothing is the resistance. Now what is the body effect? While I design a circuit in cadence, what I'll do, there is a body, I'll put into the ground. So if it is NMOS, I put into the ground. PMOS, then I'll put in the BDD. Because we have studied CMOS circuit, na? CMOS circuit we studied, CMOS we know that, please. Then what happened, in the case of this one, body is here, body I'll put into there. I put other pencil, I'll put into the BDD. So you see that, so PMOS generally we put into the NAT to BDD so that I can put the body bias 0. Here you see that inverter or amplifier with a body bias 0 body bias. Okay, so remember that in the case of any amplifier design, PMOS generally we keep NAT to BDD, and CMOS, not CMOS, a basic driver NMOS we keep into the NAT to ground to nullify the effect of body bias. Clear? Yeah. So now that's the body bias I'm saying you. This expression says the SB0, source and body. This is my source, this is my body. Should be 0, then this part completely vanish. Is it not? This and this cancel out. Then we have a simple. So no body effect. These things you should remember, please. This is basically basic structure. Already all of us know that we have taken from some books, not from Haykins, but some other books. Maybe from other books, standard books I have, I forget the name. So now already I discussed, this is the linear capacitance. These two are linearly related. But certain capacitance, those are where there is a body is there, those are parasitic capacitance, already discussed. Their expression is something different. You see that wherever there is a body effect, body effect is coming. These are basically, you see that wherever is the body, this capacitance basically parasitic capacitance, and these expressions are like this. See that. You have to calculate the expression. I hope all of you know it is minus is there, so it is 1 by. So that is the expression for parasitic capacitance. What you studied in the MOS also, in a not MOS, in a diode, I already said diode is NMOS and PMOS, and we have a channel. This channel is a parasitic capacitance. Parasitic. Parasitic capacitance. Capacitance. Okay. So those capacitance basically model is like this. So that's the device people will talk too much on that. This is the all basically circuit principles and other. Yeah, this is important part for me. That you see, this is a very simple diagram, but it implies many things to us. That if at law BDS, at law BDS, and BDS is very, very low, and transistor becomes, you see, very, very linear region. Very, very linear region. Okay, what do you mean by that? Means what? Which region it is now? Is it triad region or saturation region? We know that for saturation region, you have to have BDS should be greater than PGS minus BTM. Yeah. Now, what we understood that this is basically saturation regions. We just know condition for saturation is this one. Okay, saturation for this one. Yeah, saturation for this one. So, what we understood, if BDS is very, very low, I'm sure this equation is not being fulfilled. So, at a very, very low BDS, MOS is in triad region. And that is a linear relation. Understand my point? What I said, that for saturation region, this is the formula for saturation region. And obviously another term, BGS should be greater than BTN. This is always known. Otherwise, MOS will be off. So, but what infer from this basically equation, if law BDS, law, then this equation never be fulfilled. So law means it is in triad region. So this is the triad region. Triad region. Okay. Triad region, MOS is simply a resistance, linear resistance. I have shown you that diagram. MOS becomes a resistance. And this is the formula of this MOS is this one. On MOS in triad region, remember, MOS is in resistance. When is the triad region? Switching operation happening. There's a MOS, I'm giving a pulse. I'm giving a pulse. Okay, time pulse. And you know that every pulse I'm giving, it is around to be, say, BDD. Somewhere some voltage will be there, some BDD will be there, BDD. Whenever this is B in graph, sorry. Okay, B in graph. Yeah, whenever I give a pulse, okay, whenever I give a pulse, what will happen? MOS will be where? MOS will be in triad region. And then it offers the resistance. Nothing is there, it is off. On and off, on and off, on and off. And resistance is defined by this one. Okay. If high WYL, less resistance. If less WYL, high resistance. Point to be noted. Again, I am erasing this part. That in a pulsing design, pulsing circuit, where we call digital circuit, where we call pulsing circuit. See, we have a resistance, we have a driver. In the driver, we put what bean. Say this is a bean, and I put this is a bean, this is a graph. This is a time scale. And then I have giving a pulse at a particular moment. Okay. The moment I'm giving a pulse, the moment I'm giving a pulse, this MOS will be is in where it will be in triad region, and this is nothing GM. This is a resistance. What is the resistance equation? This is the equation. And you see that here resistance basically depend upon your overdrive voltage. This is your overdrive voltage, BOV, overdrive. BOB. And these are the technology parameter already said. So those things are very important for us. So again, I shown you that, already I said you that if I give a BB, then it will become current source, nothing a resistance. So this is the fundamental things I must know, understand. Common source, maybe you see the different configuration. Those are newcomer, please understand that this is my load, see, this is my source, this is driver, and this is also another combinations where we can see that this is a common this is source, PMOS, so it is also common source. This is also common source. This is also common source. Okay, see, because this is a PMOS circuit, and this is a drain side is here. At the drain side, I put a resistance. This is nothing resistance. Already said this is nothing resistance. This is also resistance. Okay, this is also resistance. So remember that in a PMOS circuit means this is source, this is the drain. This becomes a resistance.
স্কলারশিপ না স্টুডেন্ট পোর্টালে আপনারা না আপনার ইনস্টিটিউটের সাইন বোনাফাইড সার্টিফিকেট দিতে লাগবে সার্টিফিকেট না আমরা করে করব এটা সমস্যা কেন হ্যাঁ
Okay. Sorry. Now I understood that now this is a resistance, this is also common source. What is this? You see that this is a bean, this is a resistance, again common source. This is a bean, PMOS, this is a resistance, this is also common source. So all are common source amplifier. So you can have a different combination where you can make your common source configurations. All are common source amplifier. Please remember. So if you have any doubt, please you can ask me a question. This is all common source amplifier. Different way we have really tried to represent the things. Fine. So now,
Sir.
Yes, please.
Sir, I have a question.
Yeah, please.
What is the difference between AC ground and ground, sir?
Oh, AC ground, basically AC ground, not a virtual, is a virtual ground, basically, not a fully ground, okay?
Yes, sir.
AC ground is a virtual ground where basically high impedances are below that one, okay? Differential amplifier will find differential amplifier you will find, I'm showing you the differential amplifier you draw. Okay. In differential mode, basically there is a current source we put into there. Okay. And current source means very high impedance, very, very high. So this is open circuit conditions. If I make this open circuit condition, so that becomes a virtual ground. Okay. This is classic ground. Okay.
Yes, sir.
Fine.
Yes.
Can I proceed?
Yes, sir.
Okay, thank you, please. Thank you, Apurva, for question. Now we see that these are basically important small modeling. I'm not discussing much on that. This is the all early effect response. Yeah, this is very important for me, that I must know what is the capacitance, what is the Miller theorems, what is the poles and zeros, and what is the transfer function of a simple amplifier. Because we have written so many, any even third semester, fourth semester, we have analog circuit design, so we have to have a might have design but not consider somewhere at low frequency those capacitors are bulky open circuit. Remember, in this circuit we have shown so many capacitance, but in the low frequency these circuits are very big, becomes what? Bulky means these are open circuit. Okay, capacitance. So these are not coming at very low frequency. Okay, and what we studied in basic electronics or analog electronics basics chapters, we just take a transistor and try to design amplifier. Okay, because those days knowledge is not to that extent. So fine. Right. If we talk about frequency response, where frequency is useful, and as I said you that this amplifier is amplifier. This can be can you use it at high frequency? There are a lot of challenges to use it at high frequency. Okay, then a lot of things have to be incorporated to go into the high frequency operation. So those are basically the topic of discussions, that amplifier that I designed may work as a kilohertz range. If I want to work this circuit as a megahertz or gigahertz range, what things to be done, what things to be incorporated, or what modification to be done in the circuit so that it will work in the high frequency. On what basis it is working? How do you know that at what frequency it is working? It's a very important question. I have a design amplifier. I must know at what frequency it is working. If I do not know, I am a layman. Then I become ITI part. Okay, ITI people, they do not bother about all those things. Okay, they have a circuit design and everything is there. They do not know inside what is happening. So, but being an engineer, we must know the how at what frequency it will work. What are the constraints? Fine. So that things I'll discuss over here. Now you know that you see what they have designed in this circuit. If I see look into the circuit, I can easily say it has two poles. One pole is over here, another pole is over here. Pole means wherever there is resistance and capacitor meeting, that gives a one pole, 1 by RC. Pole means POLE, pole means that I studied in control 1 by RC. 1 by RC. 2 pi RC, whatever, 2 pi RC, whatever, you see the angular frequency. 2 pi RC. So pole is equal to, remember, pole is equal to 1 by 2 pi RC. 2 pi RC. Okay. So now I have two poles, this pole and this pole, that dictate me my frequency response. And remember, two poles very close to each other. Again, phase margin issues will come to picture. Phase margin again control or dictate your transient response of a circuit. Very important, transient response of a circuit to know. So those who dictate me. Now there are so many capacitors are there. How I can simplify the circuit? What they have done, they have used the Miller theorems. Miller theorems, okay, fine, but it's not applicable every time. But there is approximation. That is a side effect. I will explain you. By Miller's, they have reduced this. They have CGD. They have really divided into two parts. One part is coming this side. Another part they have divided into this part. So this C basically into distributed. This C basically, if I say two poles, Yeah, the C basically being this C is distributed this and this. 2C it has made. And to study it in BTech level, how this is the formula, how to transfer, this is the formula. At the output, at the input side, it comes 1 plus what is the mod of AB. And what is AB? AB equal to GMRD. What is AB? In this circuit, what AB is what? GMRD. GMRD. What is RD here? RD here 1 by GM. What is RD here? 1 by GM. Because drain and source connected is become 1 by GM. So it is say it is M GM1. Any circuit, remember, gain is 1 by GM, GM into RD, GM1. So RD means here RD means 1 by GM2, 1 by GM2. So what is my gain? Now my AB will be what in this circuit? GM2 by, GM1 by GM2 in this circuit. Okay. In this circuit, my gain will be GM by ID. So fine. If I know the GM gain, I can easily convert, I distribute the CGD into two parts. One is this part, another is this part. Okay, 1 plus mod of AB, another part is 1 plus 1 by mod of AB. So that way part we divided, and we can have two poles. One is pole there, total capacitance, total resistance. One pole over here, input poles. 2 pi. Pi means, you see, this is the pi. This is the pi. Pi means what is called RC. Tau. Tau means RC. Tau means RC. See, tau means RC. Okay, tau means RC. So that's your input pole. Pole means, as I said, you 2 pi RC. RC means they have written in this picture, we have shown tau in have written. So club together, RNC together, it gives you one pole. Output poles, you see 2 pi tau out. Tau out is this one. Okay. Again, we can calculate easily. This is what tau out. So that gives you what? And understood two frequencies. So this is the frequency response transfer function. Gain is what? GM1 by GM2. They have written GM1 by GM2. Minus is that because it's a common source amplifier. So I would have a gain minus will be there. And if I mod, then it will be GM1 by GM2. So remember, please, it is GM1, please. What is this? GM1. GM1, please. GM1 by GM2. So in this circuit, your AB is GM1 by GM2, and that's they have written gain is there, and then you have two poles, they have written their own expression. Okay, J1 F by F in F by F, two poles. So now this circuit has a two poles, you understood. Apurva, am I right? In the right direction I'm going?
Yes, sir, you are going in the right direction.
Okay. Or is it very common that I am telling?
No, sir, it is not common, that common.
Okay, please. Then I hope that this is the transfer function of a simple CS. But one thing is missing. In any common source amplifier or any amplifier, there are two things. Basically, I just remove all those. Okay, keep it same. Remember, in a control system, we studied poles and zeros. There are two types of poles are there. One is called RHP pole and another is called LHP pole. Left half plane and this right half plane. What I believe, all poles must be on the left side. Okay, that's we know that all poles will be left side, so not zero, please. Poles must be what is studied in control theory, that all poles must be left side. But what is zero? Zero will be left, zero will be right. Point to be noted. Zero will be left, zero will be right. So there are two poles basically. There are two types of zeros we call. I erase this part basically. Then I have a two poles basically. No, poles not zeros. Zeros in this circuit there is a zero, but because of Miller capacitance and Miller theory applied, poles is zeros is not coming into picture, but zeros is hidden over here. So remember. In a control circuit, we studied poles and we studied zeros also. Okay, we got in this circuit there are two poles and one zero is not showing because of Miller's theorems. So I'll see where the zero is located. So zero basically two location. What is studied in control theory? That this is del and this is your j of omega. You remember? And we expect the all poles should be left side. All poles may be left side. Okay, that is expect for stability. But 0 may be here, 0 may be here, 0 may be here also accepted. I believe you whether you remember or not. 0 anywhere is accepted. So these zeros are called RHP 0. Please what's called RHP 0. And what is this 0? It's called LHP 0. LHP 0. So please point to note it. That there are two types of zeros, very significant in transient response. Transient response. The zeros are coming into picture, and we have to address those zeros into effect. So remember, if I use Miller's theorem, since Miller is the approximation theory, and the knowledge of this what is called zeros is not coming into in the transfer function. This is very, very simple transfer functions. But if I do the circuit theory, as electrical circuit theory that we do, or KVL expression, KVL theory applied over this circuit, KVL, and then obviously my actual equation will come into picture, where 0 will come into picture. Okay, there are two types of 0, RSP 0, LSP 0. First, I must understand what is the effect of my RSP 0, why RSP 0 is coming, or why LSP 0. LSP 0, no effect. It has no effect. It can in the left side. RSP 0 has some effect in the phase margin. Okay, and transient response. Okay, that's we'll see. Okay, next we'll see. Very nice. This picture, if I enlarge this picture, you see that this is the transient response. What response? Not given. I will say the transient response. What response? Transient response of a simple amplifier. Not amplifier. I should not amplify. I should anything. Now you see that this. What are the degrees are basically? Basically, these are phase margin. Phase margin. Okay. Those are basically 45 degrees, 60 degree phase margin. Phase margin. You studied in control theory phase margin. Phase margin. Margin. M-A-R-G-I-N. So now what I understood that this is phase margin is 70 degrees is over damped. What? Damped. Very much over damped. But 60 is fine and 45 is fine. And if I take another signal like that, maybe more peaks, maybe more sharp. Okay, those maybe 10 degree phase margin, maybe 15 degree phase margin. So what we understood that very less phase margin is there is a occurrence of maximum overshoot. Okay. My desirable phase margin like that 60 to 45. Okay, much more than 60, it will be overdamped, sluggish. But less than 45, it gives you maximum overshoot. So preferably we look into the phase margin of this is my desirable phase margin. So who control my phase margin then? This question comes. Is it not? Who control my phase margin? Very important question now coming. Now this picture is basically what exactly showing you that this picture. In the last diagram, we can see that there is no knowledge of RSP 0. It shows there is no 0, only poles. But actually, if you do the calculation by using KVL or KCL, this expression will arrive. Okay, this circuit basically done for only one pole. One pole means in the input there is no resistance like that. This circuit is done for like that. I'm showing you what circuit basically they have taken. They have taken a simple circuit, is a MOS they have taken. Okay, this MOS they have taken. GM1, right? They have taken RD or what? R not. They have taken, sorry. No, not taken. So they have taken simple MOS resistance. They have not R not, and the MOS they have given MOS. This is the circuit they have considered. This is beam, For this transfer function, this one. Okay, this is also an amplifier. But what transfer from this transfer function, you see that in the upper domain, in the numerator, there is a one poles, not poles, there is a one term. This is called 0. This is called 0. And denominator, there is one poles. So there is a poles in 0. But you see that is plus means there is a negative side, means left side will come. Plus means right side will go. So that becomes RHP0, RHP0. So what you understood, in common source amplifier, basically if you do thorough analysis, thorough calculation by using capital theory, we can find out there is RHP0, and then we'll see what is the effect of RHP0. Okay, you see this expression now. Phase margin, basically you see, as I said, that total we want this much, 45 to 60. My total must be 45 to 60 range. 60. Wow, how can I achieve this 45 to 60? See, how I have so many minuses there, you see, minus. But there is a LHP0 plus. This is my good side. And otherwise, you see, a single isolated poles gives you what? 90 degree. But if those poles are very close, it's not isolated, poles and 0, then it will never give 90 degree. It will give some other value. As you studied in the books, the one poles gives you 90 degree. This is special case where it is isolated poles or isolated 0. But in the case of poles, negative 90 degree, we say isolated poles. And in the case of zeros, we call plus 90 degree phase shift. But this is all for isolated. If it is not isolated, this figure is not correct. Okay, it will be maybe 60 degree, maybe phase margin, maybe not phase margin, phase maybe 40 degree, maybe 70 degree. Okay, if it's not isolated poles and zeros. Now you see that there are terms. 100 degrees, okay, fine. Then minus is one pole. Another minus. Plus is LHP. Minus is RHP. So RHP is complicating me. All negative terms are coming. Poles is giving me negative, fine. 0 is giving positive. But RHP 0 giving me again negative. So I complicated to balance my 45 to 60 degree. Getting my point or not? Please, that phase margin I have to maintain 40 to 45 to 60 degree because to maintain my transient response or to avoid maximum overshoot. To do that, I have to balance this expression. It is the expression shown for a circuit where there is two poles and two zeros. One is LHP0, another LHP0. So now you see that I have to balance it. So LHP0, RHP0 is complicated because it is again giving negative. So that is the side back of my RHP0. To maintain my phase margin, RHP0 is coming in negative here. So what I do, what I need to do, I need to pull some other poles and 0 out of my interested region. What is UGB? Unity gain bandwidth. Unity gain bandwidth. So I have to pull, suppose this pole is complicated to me, I am unable to get this value. Say. What I'll do, I'll put this P2 far above from what is called unity gain bandwidth. All of you know unity gain bandwidth, basically a transistor and this frequency response and transfer function at very high frequency. This is called UGB, unity gain bandwidth will come. Unity gain bandwidth will come into picture at a very high frequency. I am drawing over here. Okay. At very high frequency and gain over here, and this is my UGB. And what I'll do, I can take the pole to higher distance because pole I easily calculate. What is the pole? Who control my pole? GM and CD. GCD. So I have a circuit parameter who control my poles. By changing my W by L and other, I can push the transistor in different location. Remember, that the pole basically as a different parameter. See, a pole is equal to what? What right now we have seen. A pole is equal to what? A pole is equal to, we have seen 2 pi RC. R means, you see, GM, na? GM by C. R means RC. This is my fundamental formula. But in the case of mass, R means 1 by GM. 1 by GM. Here G will come over and C. What is G? So pole is equal to, you see, how who control poles? Pole equal to G means root over mu x COX W by L into ID. Okay, and 2 pi C, something C. So my controlling parameter W and ID, W and ID, W and ID. So that way I can shift my poles and zeros as per my own choice to maintain my phase margin this much. And I'm not discussing all those because already figure of merit very important. That's time is very knocking my door. I have so many things to cover. Let me check quickly. I'm going. Figure of merit, as I said you, this is very important. FT is very important. FT I need to have, if I circuit frequency is here. If I say FT is here, FT is here, FT, where unity current gain is 1, then poles will be what? First half. Empirical formula FT by T, FT by T 2. So this is the allocation of pole, then the bandwidth will be this much. You can easily calculate. So what is the control? Who is controlling parameter? L is a controlling parameter. What L is the length of channel? So length of channel should be reduced to have high FT. If high FT, then we work in the high frequency range. So this is also very important. GFT gain GFT very important. Gain and bandwidth gain and bandwidth constant. So gain we call it as gain bandwidth product. Gain bandwidth product. So this is very important term also. It depends upon the L also. So you need to reduce L so that we can improve the gain bandwidth. So these are the circuit diagram. I have shown you how this resistance capacitance come into picture. Makes a we see equation. This S term is there. You can easily I can have my transfer function. And those parameters are very important. I have to calculate those parameters already explained, I believe. Now, this graph you see that rather than I will stay to come to this diagram, it will go better. Now, I have taken a this diagram taken from Allen book. Which book? Allen and Holberg. Please. Picture is taken from Allen and Holberg. What it says, you see that in a system there are they have taken poles. You see, initial poles is this two, and then we call pole compensation. Compensation. What is the meaning of compensation? Two poles are close each other, and then if each other, then we cannot maintain this one phase margin. Okay, cannot maintain phase margin. What we do? We keep them apart. See that now this is the new location, this is the new location. You get my point? Earlier it was P1, P2, P1, P2, but they have compensated. This is compensated circuit and this is the original. Then what is this? You see that. Here you see that phase margin, if you, I think you are familiar with the body plot and other, here is phase margin is 0 because you see that 0 dB line. And this is the phase plot, this is the phase plot, and this is the gain plot. Okay, this is the dot means phase plot, and this is dark one is called gain plot. Okay, so they're combined to you see that. No, sorry. You see, this is the original one, this is the compensated one, this is the original one, this is the compensated one. Please, point to be noted. Okay. This is the original one. I'll make a mark, and here is double cox. I will give it the compensated. Here is one, there is double. So this is the compensated. What is the meaning of that? You see, If I take the original one, your phase margin is 0, because you see at phase margin mean what happen when gain is 0, you have a no frequency. You see that your phase is 0, so phase margin is 0. Okay, getting my point? Phase margin is 0. Here is phase margin, how much? Phase margin is coming. Phase margin is coming. So we have to maintain the phase margin, because basically this is called frequency compensation or pull compensation, where basically we have to have phase margin. Here actually phase margin was 0, original 1. Okay. See that the moment I have a this one. I believe all of you know the how to calculate phase margin. We'll look into the where this your gain is 0. Gain is crossing 0 dB line. Gain is 0 dB line. If I gain is crossing 0 dB line, 0 dB line at this point, what is my original? Original plot is what? Original plot is you have this much. No, then both are correct. It is, oh, sorry. I have, sorry, please. My term is different, please. I do not check it. Original one, please, you should ask me question. Original is dot, okay? Deep one is the what is called compensated. This is my original, this is compensated. Please, this is compensated. Okay. Sorry. Certain. At this line, dot line, uncompensated. Okay, please. What I say may be different. Now you see, in the case of uncompensated dot line, when there is a gain is 0, this line is crossing 0 dB line here, and where is your phase margin? Because this phase is also 0 over here, so there is no phase margin. Okay, there is no phase margin. So phase margin 0 means what? There is a maximum overshoot. Please, point to be noted. Dashed line is called uncompensated, and this solid line is called compensated. If I see the dashed line, what I can find that where the moment your gain plot is crossing a 0 dB line, phase plot is 0. So there is no phase margin. So they have done some calculations, and they have used that compensation technique. They change the poles and zeros to different location, and you see finally what you have seen that in the in the compensated one there is a phase margin. Yes. Any question, please?
So 0 would also affect the phase margin?
Yeah, because you see 0 will affect, because 0 will affect, because 0 is giving you what? 0 is giving you a plus what is called phase margin, and poles is giving you negative. So the moment you do this graph is coming means what? What do meaning this? There is a what? Poles is coming, nah? Is it not?
Yes.
This location means there is a poles is coming. What do you mean by this? There is a 0 is coming.
Yes,
Okay. The poles and zeros are basically controlling your what? Entire diagram. Okay? Any question, please? So poles and zeros. Only thing is that remember, I said new terms. 0, there are two types of 0. One is called RHP 0, RSP 0, another is called LHP 0. So RSP 0 more culprit for phase margin, not phase margin, or tangent response. Okay. It gives you negative phase, just like your poles. Okay. So
Yes,
poles and 0 basically dictate your this graph, na? Clear my point?
Thank you, sir.
So
Thank you.
you can play with the poles and zeros, and then you have to maintain your phase margin, as I see 45 degree. See, unless and until you do play with there's no statistical formula, okay, to have how to split it. You have to play with your circuit designs, because circuit design you have to change your W by Ln, then poles location will be different, because pole is what? 1 by, again I see, what is pole? Pole is nothing, 1 by Gm by what? Gm by 2 pi, if I take MOS, 2 pi C, okay? Gm is what? Gm already I know that mu x, cu x, and then WL, then ID current. Okay, this is your GM. So this GM is playing into role, and this W by Ln ID is playing into role. Now I always said L is fixed and W is playing into role then. So that's entire things. How will you play with your poles and zeros? This is all about the MOS as a noise. I am not discussing all MOS differential circuit. This is very important because unless I touch on the differential amplifier, I am unable to finish my things. Okay.
So timing is running out.
Okay, I'm just I'll take you 1 minute. Just have a quick look into the circuit. Okay. Otherwise, yeah, I feel it is incomplete. Okay, I just quick look and I'll just take 1 to 2 minutes. Okay. Okay.
Okay.
Then differential circuit. Please go through the a few books. Major books I will say the Rajabi analog circuit, analog VLSI circuit, Rajabi, not microelectronics. Okay, this shows how I can nullify the effect of. You see, these are the very important parameters. This circuit is very important. Pollution, because many times we say that common mode voltage. You see that common mode voltage becomes stabilized at this point. We cannot take arbitrary voltage. We can take the common mode voltage from this to this. Okay. But we should not take common mode voltage over here because this is instability. So common mode voltage should be from this to this. And please study from Rajabi books. Rajabi, very fantastic. They have explained where we can fix your common voltage in this range. You can fix your common voltage and change. Then there are different combinations we can really work out. This is a complete differential amplifier. They have done the what is called calculations of differential mode and common mode. No time is there, so I am not just flashing, going So this is, you see that how the way we are designing the differential amplifier. There's maybe effect of capacitance also. So those are effects you need to take into consideration for. Now you see that I've written that common mode voltage become a differential. This is the most challenge things. Okay, you have a common mode, but it's become a differential mode in the circuit. This is the major drawback. That CMR what you want. That what is the CMR? You see this expression, AD by SEM. So SEM is undesirable. This is undesirable. Undesirable. So that's how we, because CM become DM. CM means common mode become DM. Common mode means noise, maybe other things. Everything is not common mode. It becomes a differential mode at the output. That becomes a nuisance for us. Okay, undesirable. That should be reduced. That's things we discuss about here. Headroom analysis. Please, different circuit. Okay, please. You see that this is a Gilbert cell. This is all extension of your common mode voltage amplifier and not differential amplifier. From there, you can have a Gilbert cell. Gilbert cell basically is a multiplier, analog multiplier. We can use circuit as a multiplier. So this is a big challenge, but big important things, because for any computation you need multiplier. Okay, so Gilbert cell is a basic multiplier blocks that we can design from the differential amplifier, and that's I have given no time now. Yeah, you see, this is the basically, as I said you, this is a one OTA and two OTA back to back is become inductor. See, this becomes inductor. This is called active inductor. What inductor? Please, active inductor. Why not coming? Sorry, please. Yeah, this become an active inverter. Active inverter, inductor. So please study active inductor from books, other books. So that's, you see that the moment OTA design in this fashion becomes a what? Inductor. So now, thank you all. Now I'll just show what exactly circuit design we have designed NRD Silchar. We have our whole chips. We designed 3 chips. I have just shown you 3 chips. One is basically analog front end for the pre-amplifier speech recognition systems. Then we design another is called what is called pre-amplifier for main machine interface. One more circuit is there, chips. So we have our 3 chips and Silchars. We have our backend engineer. We design our own chips. Chips are designed in the Chandigarh Mohali. So any doubt? Thank you all for any questions I am had to have. about to, yeah, about to, I think I'm just stopping my presentation mode. Time is already far. So about to, I think Dr. Apurva, one question hour, please. Thank you, everyone, please, for listening me, giving your time to our time, really listening, big challenge. Yeah.
Thank you for your informative talk. I would like to request the participants to raise a few questions if they have. Otherwise, we will wind up this session and continue tomorrow.
Yeah. Yeah. Any question from audience, please? Yeah, Apurva, your audience is silent. Huh? No, I think they either they understood everything or they do not understand anything. Okay. Morning session. Yeah.
Okay, sir. They have no questions, so we will continue tomorrow. Tomorrow morning, we will have Jatana sir, who will deliver a talk on
Chip design.
physical design. Physical design.
Yeah. Basically, we design chip from the Mahali. Jatani sir is our partner for that. Thank you, then everyone. Thank you, Dr. Apurva, for giving me chance to share my knowledge to dear friends. Looking forward more collaborations.
Thank you, sir. Thank you.
Thank you, everyone. Thank you, everyone, please. Namaste. Everyone,
Thank you.
please, namaste.